If a tree falls in a forest and no one is around to process its existence, does it even bother to render? We operate under the assumption that reality is a persistent place. We assume the chair behind you, the surface of Mars, and the core of the Earth all exist exactly as they are, whether you are looking at them or not. Zoom down to the subatomic level, and that assumption breaks down. In the quantum realm, particles lack fixed positions. They exist as hazy clouds of probability, floating in multiple potential states at once, until an instrument forces them to pick a location. Classical physics has struggled to find a physical mechanism that explains why a particle picks a definitive location only at the moment it is measured. The confusion stems from treating this as a physical problem. These subatomic puzzles become logical when analyzed through the lens of computer science. Every computational system shares one strict boundary: finite processing power. A system can only track so much data at once before the hardware overloads. Video games manage this limitation through a strategy called render distance. To save energy, the engine only generates high-resolution terrain inside the player's immediate field of vision. Everything behind the camera reverts to compressed data, acting as a placeholder until the player spins around. If the universe operates on a similar architectural logic, it would follow the same efficiency rules. Keeping unobserved quantum particles in a vague state of probability requires vastly less computational energy than tracking the precise physical coordinates of trillions of particles simultaneously. The moment a human or an instrument observes a particle, the universe is forced to calculate an exact state and load the physical coordinates on demand. The observer effect functions as a strict resource-saving algorithm designed to keep the universe running efficiently. A framework published by the Santa Fe Institute in late 2025 provides a mathematical basis for this efficiency model. Researchers analyzed the simulation hypothesis through the hard limits of computer science, testing what it would actually take to process our entire reality. This chart shows the impossibility of rendering a continuous absolute state for every particle. The processing demands reach a system overload no hardware could sustain. The theoretical alternative leaves non-critical particles unresolved until interaction, dropping the load to a manageable baseline. The bizarre rules of quantum mechanics match the exact architectural requirements of a simulated reality running on finite hardware. This behavior extends beyond subatomic particles. We find similar signatures in the hard-coded mathematical constants that define our physical limits. Physics focuses on the fine structure constant, a number roughly equal to 1/137. This figure dictates how light and matter interact, setting the fundamental resolution of the universe. If we move to 138, one tick past this constant, the interaction between light and matter changes. This represents the theoretical boundary wall where the universe's physics engine can no longer maintain structural integrity. If the universe reallocates its processing power to manage these boundaries, we might expect to see anomalies in the data storage of high-level observers. The Mandela Effect, collective memories of a history that never happened, suggests a potential drift between the current rendered state and the previous save file. These collective false memories appear as the residue left behind after the reality engine undergoes a background update. The universe generates in real time as an active engine. Looking through a telescope or a microscope is an act of forcing the cosmic computer to load the world.